So, hi everyone. I hope the break was successful and we have stretched our legs and backs and we are full of power to listen to our keynote. Well, let me tell a couple of words about our keynote speaker. Two things, one about the background and the other one about the contributions to science. As for the background, Professor Kees van Dinter it comes from the Netherlands, did a PhD in 91 at the University of Amsterdam, wrote a legendary PhD thesis on the composition of meaning, which I actually launched the whole research on semantics of ambiguity and semantics of vagueness. Then other stages in his academic career was Philips Labs in Eindhoven, then Stanford University, then also University of Brighton, and then a longer period at the King's College, University of Aberdeen. And finally, well, the current position of Professor Van Linden is Utrecht University, Department of Information Computing Sciences. Well, I have to say that basically most of the prominent journals are in the list of membership as a real board member of Professor Van Diemter, so computational linguistics, semantics and pragmatics, journal of semantics. These are the top journals in the field. Also, there is the Baltic International Yearbook of Cognition. Well, fair enough. So really super decent journals. And anyway, so that's about the background. But so why Professor Kees van Diemter is really awesome in science, and why I'm so delighted and honored that he will deliver his keynote speech in our today's CogSci session, because he contributed significantly in the research on ambiguity resolution, vagueness resolution, and not just computer science, not just logic and formal semantics, but also with huge impact on psychology. And there is a principle of idiosyncratic interpretation that communication sciences people know. This is also something that comes from Kees' work. And yeah, anaphoric relations and lots of superb, interesting fields that are activated and reshaped because of the work of Kees. And then the second large field where his contributions are incredible, I must say, I don't know a single other colleague, is the work on referential expressions. And referential expressions, I mentioned anaphoric relations, but this is a bit wider topic. And last but not the least, I would say Kees van Diemter is really a kind of prototype of a cognitive scientist, because he kind of integrates a logical background, linguistics, formal semantics, computer science, artificial intelligence, and psychology. These are the fields that are naturally in the work by Kees. Well, without wasting more time, I'm super delighted and honored to give the floor to Kees. And yeah, the floor is yours.
Well, thanks very much, Jurgis. That's a lot to live up to. I'm not sure that I'll be able to, but I'll certainly try. Before starting my talk properly, and I'm looking at now at the interface, it's a little bit difficult for me to see now, but I'd like to have some indication. Who of you are into deep learning and neural algorithms? And maybe, Jurgis, you can watch the chat to see how many people say yes to that. Is it no one at all, or is it just a few, or is it more or less everyone? So neural or deep learning algorithms.
Do this microphone. What is what you don't, we don't hear you.
Okay, thank you. So how many people were they? Just
So
one.
there was one that
Good,
was
good, good.
indicated. I was just my micro was muted, therefore the
Okay.
problem. So anyway, so the one is
Sure.
into that, but there are other colleagues. So just I think one is really in kind of into that, but there are
Okay,
other
good. Yeah.
colleagues.
So one more similar question. How many of you are into Bayesian models of any kind?
None, as far as I
None.
see.
Okay.
At least I heard about it. I can't say I'm deep in it, but we had it in the lecture. Yeah.
That's a half. I'll count that as a half. Okay. Right.
Okay.
Right. That's good to know. Very useful. All right. So I'd like to talk about dimensions of explanatory value in computational models of natural language use. That's a bit of a mouthful. Let me unpack that a little. What the talk is going to be about is there are all kinds of models around in cognitive science and AI of language use. And I'm going to ask what is the explanatory value of these models. And although I'll be focusing on these models of language use, so broadly NLP models, right? Natural language processing models, I secretly think that the bulk of what I'll be saying will generalize to many other models in AI and or cognitive science. Now, my talk is going to be based broadly on the paper that I'm listing there below, my 2023 paper in computational linguistics. And as you can see from the title of that journal, that's for an NLP audience, yeah? Now, so one thing I'll be curious about today is what you as cognitive science people think. So my last slide will be sort of back over to you, how you see these things that I'll be talking about, things to do with explanatory value. I start with a little anecdote. A few years ago, some colleagues and I submitted a paper to a journal. This was about some new NLP model, and we claimed in the paper, on the basis of experiments, that our model outperforms other models, right? Has better performance than other models. We got the reviews back, and they were mostly very positive, but one reviewer argued along the following lines. They say, yes, your model has better performance, but it's less explanatory than a certain model X. Possibly a model of their own, but that doesn't really matter, does it? Now, that argument from that reviewer, so the paper was ultimately accepted, and right, but that argument has always fascinated me, and I kept thinking about it, because what is explanatory value really? How does it relate to performance? Is it something entirely different or the same and more? And of course, then how important is it, right? Compared to other aspects of performance, if you like. So what I ended up doing after some, let's say, failed attempts is go back all the way to a very old set of ideas in the philosophy of science. They're known under various names. One of them is the Hempel-Oppenheimer model. The other is the deductive nomological approach towards explanation in science, right? Now let's talk a little bit about what that model is. Suppose we want to explain someone's chess move. Note that I'm not talking about something in physics, right? And all these ideas in philosophy of science tend to think primarily of physics. But we today will be talking about human behavior. So let's think about a chess move. Tim plays a certain chess move, let's say X. Now, suppose X is the very best move that Tim could have done. perhaps it's immediately checkmate, and there's no other way to checkmate. Then what's a good answer to the question, why did Tim play axe? Well, that's easy, isn't it? You can simply say, Tim did it because he's rational, right? Essentially, you're saying, Tim always makes the best move. This is the best move, and that's why he did it. Right? Good explanation, isn't it? Now let's look at that through the lens of the DN model, right? Deductive nomological approach. That approach consists of two rules. The first rule is that the observations, so here that's the move, must follow logically from the explanation. Now, that's absolutely fine, isn't it? Because if the explanation says Tim is always fully rational, then yes, right? The fact that he makes this move follows logically because it's unique best move. But the DN approach has a second rule, and it says that the explanation must be true. Now, that's more problematic, isn't it? Because is it true that Tim is fully rational always? Well, that would be a little bit surprising, wouldn't it? Who of us is always fully rational? Suppose the situation on the chessboard didn't allow a checkmate in 1, but a checkmate in 10, right? In that case, do we really think Tim would have necessarily found that move? No. So this shows you how the deductive nomological approach thinks, right? So you have a law, if you like, from which you try to explain observations, and the observations need to follow from that law, and the law needs to be true. Now, of course, probably in my topic, the things that I work on, and probably the things that you work on as well, truth and following from needs to be taken with a little bit of a pinch of salt, right? Because most of our models are probabilistic these days. Well, that can be fitted into the deductive nomological approach because that one has a probabilistic version. And you see that there on this slide underneath the text in black. The text in black is what I just told you about truth and following from. And the probabilistic versions make that, well, probabilistic. So the second rule now says that the model must have high probability. The first rule says that given the model, the observations must have high probability, right? So conditional probability as written there in red, right? So from right to left, if you like. So if the model is true, what's the probability of the observation? So in my example with chess, it was just one observation, remember? But it could, of course, be many more. So that now is what we'll understand as the deductive nomological approach. All right, so if we apply that idea to natural language processing, then basically that first rule is about performance, is about the extent to which the model predicts the data correctly. In other words, this is something we're all very familiar with. You have a model, it makes predictions, and you measure to what extent these predictions are right. Of course, in practice, this is not easy. You can, in NLP, or I write there NLG because in a while I'll be focusing on natural language generation models in particular, but it's true more generally for all of NLP. You can measure performance in lots of different ways. You can look at similarity with a corpus, and then using metrics like blue or rouge or whatever they're called. Or you can ask human judgment, like I'm generating a text. How clear is the text? How fluent? How grammatical, right? or sometimes we investigate human task performance, right? You give a doctor advice using an NLP system. How good is that advice? How good are the actions of the doctor? All these things are being done, and we're very familiar with them. Is this reasonably considered to be an aspect of explanation? I would say yes. If model A has better performance on data than B, then other things being equal, right? A explains the data better than B. So far, so good, nothing new. If you dive a little bit more deeply into it, you will find some new stuff, because performance has to include much more than just one experiment about one domain and one language. If you're truly interested whether a given approach to, let's say, an AFRA resolution, right, something like that, works, then you need to replicate your experiment. There's a very nice paper by Belz et al. Showing how important replication is, because it often doesn't work out. And if you're truly curious, you want to generalize to different domains, genres, and languages. Again, about that as well, there's a very nice overview paper by Hupkes et al., looking at all these different ways in which one might like to generalize an NLP model. Now, the bit at the bottom goes back to my question at the start, how fond you are of Bayesian ways of thinking, right? I take it that none of you is all that taken with them. Having said that, of course, if you do several experiments, you can still think about those and their relation to the model in a very similar way, right? You do there's a sequence of observations, and you're ultimately interested in what's the likelihood, what's the probability of my model given all those observations. And if you're worried about the fact that I'm swapping around the conditional probabilities, then ask me about that later. Now, how about that second rule of the deductive nomological model? Well, a model can be true or false. Well, that's a bit naive, right? Can be plausible or implausible, even before you've done an experiment. Why? Well, there might be theoretical considerations. We'll get to that in a second. Let's first coin a term. We'll call this theory support, right? So that's the probability that your model has before you've seen any data. A Bayesian would speak of the a priori probability of the model. Bayesians find this very, very important and repeat all the time that you shouldn't just look at experiments, but also at all the other available evidence about a model or theory. So what can this look like in practice? Well, for example, suppose you have a model and it's a caption generation model, okay? The kind of AI model that, given a picture, gives it a nice bit of text underneath it that covers the content of the picture. These caption generation models, you can measure the performance in all kinds of ways. And suppose you have good performance for your model, then theory support can entail things like probe into whether your model actually recognizes all the objects in the picture, right? Because you might have a nice caption like two people on the beach, right? But you would like to know whether the model actually recognizes those people, doesn't recognize any things that are not in the picture. Things like that are called probing. perhaps a little bit closer to home, to your own interests, perhaps. Suppose you have a different model. You have a model of pronoun use in English, right? Then probing can mean testing whether your model knows what objects were mentioned in the previous sentence. Little probes like that can boost your confidence in the model, or the opposite, right? If the model cannot do it, which means that they reached their success, as measured by performance, by some sort of luck. It can also be other kind of theory support of a more intuitive nature. And this gets at the second part of my talk, where we'll be looking at two specific models and apply these ideas that have to do with explanatory value. So what I'm just saying here in this little sneak preview on this slide is some of you will be familiar with RSA, Rational Speech Act theory. That theory acts on the basis that people always behave rationally. Well, that's sort of nice, isn't it? Because there is obviously something rational in the behavior of people. We all know that. So if that explains, right, if that predicts certain facts, then you don't only have good numbers, good performance numbers, but you also say, I understand why these people behave as they do, because it's rational. Okay, so those are some very different ways in which a model or a theory can receive theory support. So that's my first dimension of explanatory value. But there's much more. How about parsimony, right? Parsimony goes under different names in different fields. Some people call it simplicity. A model needs to be simple as possible, as simple as compatible with the observations. A model needs to be elegant. Occam's razor also comes into it. Of course, all these notions have slightly different meanings and look at slightly different, often, aspects of theory. I'm not going to legislate on that. I'm just here using parsimony as an umbrella term for all of these. So for the moment, let's assume parsimony means something like use the minimum of rules and postulates and a formalism that's as weak and simple as possible. Once again, this can apply to different aspects of it. For example, so suppose we're looking at a grammar, right? If you have two grammars to describe a certain language fragment, if one has fewer rules, or fewer and simpler rules, then that makes it preferable, doesn't it? That's a kind of parser. If you want to explain human reasoning, and you can do it with predicate logic or with something far more complicated using types and higher order something, right? Which do you prefer? If the predictions in the numbers, the performance numbers, are the same. Obviously, the simplest formalism. If you like neural models, then you want to minimize training data, minimize the number of epochs, minimize the number of parameters. You see? Different types of models, different ways in which you can think about simplifying them. Why parsimony? Why is simple good? Well, suppose, think about chess again. Chess is a finite game. I don't know if you know, but because of some finesses in the rules, there's a finite number of chess games. Very large, of course, but finite. So in principle, you could have a computer program that is just a lookup table that gives you for every position on the chessboard the best move, right? Some positions, like here, position 1 and position 3, might have the same best move 1 here, right? But suppose there was that kind of lookup table. Your model is a looked up table like that. Is that what you want? Is that what you want in science? I suggest no. You don't just want an enumeration of all the data. You want reduction of data, because I'm not going to say exactly what explanation is, because no one really knows, but surely reduction of data must be an aspect of it. Now, in other areas, there's often been a huge debate about parsimony, particularly in physics, because on the one hand, parsimony, often under the name of elegance, is very often invoked. People have written books about it, and it's thought to be a very important steering mechanism to decide between different theories in physics. But recently, fairly recently, a famous physicist called Hossenfelder has written a book in which she argued that physics has relied on elegance far too much, right? In the introduction, she asks sort of simple questions like, why would God have created the universe simple, right? So nothing is easy here. How about parsimony in closer to the kinds of theories and models I'm talking about today in linguistics and NLP? Well, as I told you a minute ago, parsimony is implicit in a lot of formal linguistics. So I learned my Chomsky style formal grammar from a book by Agmajian and Heaney. And from page 1 almost, they insist on always finding the simplest grammar, and they tell you what simplest means according to them. In today's NLP, people don't talk that much about parsimony, but they do talk about it a little bit from very different perspectives. For example, from the perspective that if you communicate a model, then maybe you want to omit some of it. So can you sort of make an algorithm, and in goes an NLP model with a certain performance, and out comes a much simpler model that has roughly the same performance. So a lot of people work on that. There's also a lot of people who think about a much more practical aspect, namely energy consumption. You may have heard that the training of modern NLP algorithms is extremely energy consuming. So one training apparently is equivalent to something like a transatlantic flight. So this is training, right? Not the use of the model. Nonetheless, it's significant. So some people have thought about parsimony in linguistics and NLP, but it's never been made part of a larger story. How do you compute the simplicity of a model? Well, a really interesting school of thought in Bayesian thinking. I don't know how much you know about this, but there is a notion called Solomonov's prior, and it's basically the idea that if you want to compare two algorithms, then try to find a canonical way to write them down. And because you have a canonical way, you can compare the length of the two algorithms, right? And in that way, you can say which of the two is simpler. And the nice thing is that you can do this even across models that look extremely differently, right? One might be rule-based, the other might be deep learning. Right, so that's the theory part of what I'm having to say. Now we get to the second part of my talk, where I want to look at two models for referring expressions generation. I will tell you what referring expressions generation is. I'll introduce two models, and I'll talk about these models in the terms that we have talked about so far. Performance, parsimony, and theory support. Before I go on, are there any urgent questions? Is everything more or less clear?
Yeah, nothing urgent. I would have a question about the spatial network and tools about it.
Okay,
Yeah, but maybe that can be postponed to the end.
Yes, it sounds like it. It sounds like it.
Yeah.
You remind
Okay.
me. Yes, please. Thanks. Okay, so let's go back to that opening anecdote about that paper that we submitted. So actually, that paper was about referring expressions generation, which we abbreviate henceforth as REG, referring expressions generation. I think most of you will be familiar with the notion of reference. To refer is to anchor our utterance to things that we talk about. It's been studied in many fields, in NLP since something like the 1970s. If you know older stuff, then let me know. But in linguistics, in psychology, in speech science, actually, in philosophy, ever since Frege. So the nice thing about that is that when you apply the, well, Frege, of course, wasn't dealing in algorithms and the question of how people actually use referring expressions so much. But lots of other models and theories have focused on that. And that's really nice because now we can compare theories and models of different kinds, which are trying to do the same thing. I'll be talking about two kinds of REG. One-shot REG, where the task is simply to identify an object, as if there had never been anything had ever been said before. And the other type, the second type, is referring expressions in context, for example, in dialogue. Okay, one-shot referring expression. So reference out of the blue. Let's talk about a well-known model, the Rational Speech Act, Frank and Goodman, 2012. There are refinements of this model, as some of you might know. We could talk about those, but it will only complicate the story and not add very much. Okay, so RSA basically says the speaker and hearer act rationally. If you focus on the speaker, then in reference, that means that the speaker tries to optimize the probability of correct interpretation. So here you see that in a little formula. So in a context C, and given a referent R, then the word W, so they think in terms of words, so a speaker choosing words. So the probability of choosing the word W is, as you see there on the right. So in 1 divided by the number of things for which W is true. Don't watch the thing below the line there too much, because that's just a normalizing term, which is the same regardless on what word you're focusing. In other words, what this says is that if one word is true for twice as many objects in the domain as the other, that makes that word twice as bad as the other, because you're excluding only half the number of distractors. You get it? You want to refer to a referent R, and you want a term, of course, W, which is true of R, and as few as possible other things, right? A very simple idea. It's all about discriminatory power. choose the word that has the greatest discriminatory power while still being true of the referent. It's sort of rationality in terms of utility for the hearer. Because if you give the hearer a word that's true for many objects, then that's not so useful, right? Because then the hearer still needs to find out which of all these objects is the intended one. Okay, as I said, later RSA models are more sophisticated, and we can talk about them if you like. So that's one model that we're going to talk about. The other model is a member of this wider family, in which, so I call them the classic NLG models, in which discriminatory power plays a much more limited role. So the idea here is that if you choose as a speaker between different properties, different words to use, then that's not just a matter of rationality, of choosing the word that singles out the referent in the best possible way. There's also inbuilt issues to do with the salience of that word. So, for example, psychologists have found that colors somehow come very naturally to us when we observe and when we speak, regardless of how many distractors we remove when we use that color term. Let's zoom in on one particular representative of this class of models, the Pro model, which we published in 2019. So here you see those we, who those we are, in which I told you from the start in that small anecdote. So pro means probabilistic referential overspecification. In a nutshell, here's how the algorithm works. If some of the details escape you here, that's probably not too bad. When we apply the terms from the first half of our talk to these two models, you'll probably see why that pans out in the way that it does. Okay, in a nutshell, nonetheless, the Pro algorithm first asks, is there one single property, perhaps, that on its own identifies the referent, right? Let's say there's only one table in the room, then the word table would be good, right? You don't need anything else. You're done. If that's not the case, though, you're in a more complicated situation in which heuristics are starting to play a role. All this is based on years of experimentation, right? So the idea there is that if one property won't do it, then you try one by one properties based on their a priori probability, right? As in, start checking whether a color term rules out any distractors, right? Whether any color term is useful for you. If so, include it, right? Then you add further properties once you're done, once you've ruled out all the distractors, and it should really be now clear for the hearer, you're not necessarily done. Because there's a parameter y that tells you the probability of then going on for a little bit. Because experiments have shown us that people are often not minimal in their referring expressions. They do go on a bit sometimes. So in a nutshell, right, so that was the broad structure of the algorithm. I can give you the pseudocode if you like, but this is basically what's going on. The first of the three bullets looks at discriminatory power, but only in a very specific situation. The second bullet is all about that preference, that inbuilt preference that have over some properties, for some properties over others. And the third one is more of that same thing, property preference, but doing more of it than is strictly necessary to identify the referent. So that's what we call overspecification. Hence the name of the model, probabilistic referential overspecification. This famous parameter y right? Which is about, do I go on adding another property to my referring expression, is influenced by various factors. For example, how fault critical is the situation in which you are? How complex is the scene where you are? Lots of research into those issues. Now, let me show you how performance pans out, right? So first we do performance and then the other dimensions. And hopefully now these abstract notions will come to life. This is, of course, only one experiment, but it's a pretty crucial one, and I think it was a nice one. The scenes that, to which we our subjects, in which our subjects were asked to refer to objects, were always very small here. Always three things. So this slide focuses on the case where these things are candles, right? So figure 1a would be one scene that someone sees on their screen when they're asked to refer to the thing in a red circle. Now, notice that 1a, b, and c are interestingly different, because in scenes of type 1a, size alone will do the trick. You see that? Because there's only one small object. Color wouldn't do, right? Because that object is gray and there are more than one objects that are gray. 1b is the opposite. There, color alone will do it, because there's only one gray object. In 1c, you have a real choice. Color will do it, size will do it. One gray candle, there's only one small candle. Now let's look at some predictions. The bottom one is probably intuitively easiest. What does RSA predict? Well, of course, since the discriminatory power of size and color is the same in this case, both rule out two distractors. The chance of using one of them is 0.5, and the chance of using the other one is 0.5. No difference whatsoever. In the other two situations, one of the two rules out twice as many distractors as the other, right? Namely 2 versus 1. Hence those numbers that you see, 0.67, 0.33. Those are the predictions of RSA. Looking at that for a second, does this look at all plausible to you? You don't need to tell me, but just ask yourself, does it look roughly plausible? Okay, we go over to the results of the experiments so that you can compare the results with your own expectation. Let's zoom in, for example, again on that situation at the bottom, 1c, an expression like the small candle. So small is predicted to have a probability of 0.5. Note, right? So we call this condition the C plus S, color plus size condition, because both are equally probable. Both are able to single out the referent. Okay, so C plus S, that's the top third of our of that table over there. What is so here you see, right, on the left, again, that RSA prediction, so size has a probability of 0.5. And what do you see in the experiment? It has almost no probability at all. It is an extremely low probability, right? Wildly different from what RSA predicts. The pro model doesn't get it right either, but it is an awful lot closer. Similar things hold for the other two conditions, in which either size, S, or C manages to single out the referent. So, for example, suppose, right, bottom third, color alone can single out the reference, the referent and size cannot, then RSA tells you that that size has a probability of 0.33, whereas in fact this is something that people never do, right? If color does the trick, they will never use size. Okay, the details here don't matter so much, but it's completely evident that the performance of RSA is not good, whereas the performance of Pro is, well, not so bad at all, I would say. But that's not the end of the story. I'm not going to tell you sort of a victory story like we're better than them. So here's a story that I do, the beginning of the story that I do want to tell. The RSA model has low performance. On the other hand, it's very parsimonious, isn't it? That little formula with a sigma in it is pretty simple if that's all you need to make these difficult decisions. Theory support, we talked about that before, didn't we? It's all about rationality. RSA may not always get it right, but it doesn't need any fiddling. It just says people do what they should do, right? That's rather nice, isn't it? Compare that to Pro, very different picture. I think it's fair to say that performance is very high. Parsimony, well, if I showed you the pseudocode, it fits on 2 pages of this screen, okay, in a font that's still legible, but it's not super simple. Theory support, well, we can talk a little bit about that. It's not so easy, perhaps. But looking at this, you can understand our reviewer, can't you? They basically say your model is ugly. A lot of you will know this book, Thinking Fast, Thinking Slow, in which all kinds of obstacles against naive rationality are discussed. Shortcuts, optimism bias, anchoring. Recent research on referring expressions has shown that all of them are relevant. When people refer, they make shortcuts. For example, my colleague Guanyi Chen found that referring expressions in experiments are much more often unclear, so under-specified, than had been reported so far, in a strange oversight of lots of researchers, including myself. Optimism bias. Some of you may know the Fussell and Krauss work, where speakers who need to point out a location in New York to a speaker tend to assume all kinds of things known just because they themselves know it. Anchoring, right? If your interlocutor has used a certain expression, a certain property like red, you're more likely to do it as well. Perceptually salient properties are used with much more likelihood than discriminatory power analysis would predict. So my claim is that an explanation-based comparison allows us to see much more clearly than before how RSA and Pro differ. Jurgis, given the time, I can do 2 things. I can spend 5 minutes telling you how this comparison pans out if you look at this other type of RAG, where you look at context. It will be a different picture, just using the same dimensions of explanatory power again. Or I can skip that bit and stick more closely to my allotted time. What do you recommend?
I think you could do the full version because I think the narrative is fascinating. If and probably with the
Well, fantastic. I'll do that then. So that means that I'll probably be done in 10 minutes, right?
okay.
Thank you. So now REG in context. So that's about what we all know. You write a story, let's say you've introduced a certain person, and now in the next sentence, how do you refer to that person? Proper name or description or pronoun and all that, right? So there are lots of models that try to make good predictions about how human speakers do that. So with a number of colleagues, with Fafa Same and Guanyi Chen, whom I mentioned before, we compared 7 models. 2 rule-based models, 2 machine learning models that use features like did the referent occur in the previous sentence, right? That sort of thing. So linguistically informed, if you like, machine learning. And then 3 neural model, recent stuff, fairly recent stuff. And what we found is that, in a nutshell, some very parsimonious models turned out to have great performance and theory support. So that led us to paper titles like non-neural models matter, right? Because they can, if you look at all the aspects, they can do rather well. Here in slightly more detail, so these machine learning models, which used features like, did the referent occur in the previous sentence? Is it animated or not? And all that, right? Is it in subject position, right? Like 10 to 20 features. Their performance is really high, actually better than neural models. Replicability and generalizations is very high because a lot of work has been done on it. Some of you might even be familiar with these evaluation campaigns in which that was undertaken, all that work. Theory support must be regarded as high because factors like recency, animacy, competition have been studied by linguists for a long time. So if they then give you good performance, right? That doesn't feel like a coincidence, right? You have this theory in addition to the numbers. And the parsimony, well, bit nuanced because some of these models use lots of features, whereas others are quite parsimonious about that. Compare that to the neural models. Performance was not as good as we had expected. These models have not been around for very long, so there's not a lot of replication and generalization. Here you might shout, now you're being unfair because you're using the fact that these models are so young. So of course they have, okay, fair enough. That's perhaps a little bit, right? Yeah, how can you compare a young theory with an old one? That's sometimes unfair. Just like, 2 people apply for a job and one's much more experienced than the other. Difficult comparison. Theory support for neural models. Well, that's a can of worms, right? Let's not go there unless one of you is going to ask me later. Parsimony must count as very, very low, right? These models have billions of hyperparameters. So, well, what can we say? So, my summary. I've proposed a set of dimensions along which natural language processing models can differ. These dimensions were derived from probabilistic Hempel-Oppenheimer explanatory value. We looked at how these dimensions pan out when you apply them to 2 kinds of REG models, one-shot referring expressions and referring expressions in context, right? Models of how people do this. And we reach the following conclusions. 2 slides. First, NLP models in the literature are typically only evaluated on their performance, with very little attention for theory support and parsimony, except hidden away in some statements somewhere, sometimes. My claim would be that we can't afford to discard these crucial aspects of scientific explanation. If we could, we would be the only science that can, right? Because other sciences use this a lot. If we don't do that, we risk making models that are wrong, right? Because they overlook the a priori probability of our models. Myopic, right? Because they look at not enough deep data. Unwieldy, because they're not parsimonious. And merely descriptive, because they might just sum up observations rather than explain. Second, again, mind you, in my examples, I'm not trying to say our own model is superior to other people's models. Rather, I'm saying when you ask these questions about which is better, you need to look at many different facets and separate them, not try to be monolithic in your judgment. Learn to say model outperforms model B, but B is more parsimonious and has more theory support. Things like that. What does this all mean for our field? Well, it would be nice if conferences learn to ask people when they submit a model and paper that tells you about how the model is evaluated, not just give performance numbers, but give something like a model card. And here is, we're not going to read this from start to finish, but so you would first have to say what's the aim of the model, then talk about replication, of course, performance, replication, generalization, theory support, which is called here indirect support. Sorry for that change of terms, and parsimony. So I think that would be really good if readers were systematically made aware of these dimensions along which models can differ. Now, as I promised, back to you guys. You represent a slightly different community than the community for which this research was originally done. So first of all, how do you feel about this notion of explanatory value? Do you think it's far less important than performance, novelty, explainability, practical applicability? And then if you believe that I'm onto something, then how would you weigh these different dimensions? How would you compare performance, theory support, and parsimony? So that's my question to you, in case you don't have any questions for me.
Well, thank you so much. Thanks, Keith. That was very, very important and wonderful talk. And so now it's the floor for questions, comments, any sort of disagreements. So do we have any comments or anything to...
I saw a hand raised. Wolf Harder.
Wolf?
Yeah, yeah.
Go ahead.
I have 3 questions, if you allow me. First of all, aren't Bayesian models suitable to apply on small data sets? We had this topic earlier today. But I remember just when I was studying this topic that they are suitable to also to work with small data sets, so that we don't need large data sets.
when you say work, you mean they can be learned from small data?
Yeah.
Yes,
Yes.
you're
Yes.
absolutely right about that. So in that sense, too, they are parsimonious. Yes. Now, of course, that is a claim that should be related to performance, right? It's not a big achievement to achieve lousy performance based on few data, right? It would be
Mm.
it would be something if you had good performance based on not a lot of data.
So maybe that would solve your problem, Yogis, we talked about. So maybe it's worth to try it.
Sorry, how do you mean?
No, we had earlier the topic after one
Oh,
talk today and
okay.
about size of data sets. My next question would be, do you have some experience with this Python library PyMC? It's a probabilistic programming library for Python that allows users to build Bayesian models with a
Oh,
simple
yes,
Python API and fit them using Markov chain Monte Carlo methods.
I have heard a talk about it, never worked with it myself. Why do you bring it
Mm.
up?
Yeah, maybe this would be a good tool to try to work with for the cognitive guys here. I
Okay,
don't have any experience. I
but
just
that's
wanted.
not.
Okay, you have heard about, but you didn't try it yet. Okay.
But is that point related to dimensions of explanatory value or?
Yeah, and in general, to find structures in hidden structures in data sets. So yeah, it's one of there are quite many tools, but this was about Bayesian models, so that's why I'm asking. Hmm. No, okay. If you didn't work with it, then I think this is answered. And my last question is theoretical. Yeah, you mentioned Solomonov's prior. Um, I had an association Kolmogorov complexity.
Yeah,
I guess it's directly related. Yeah,
indeed,
probably.
indeed.
Yeah. Okay, so we can calculate one from the other, and
Yes, I think they're
okay. Yeah,
they're very similar notions, aren't they? Yes.
I see. I see. Okay. Okay. Thank you.
Um,
And thank you for your talk, of course.
Well, thanks. So any other questions or comments or anything to be added? I'm kind of fascinated by the idea that people are trying to evaluate approaches just by focusing on the performance or by focusing on the simplicity of explanation. But I think this the the point that you were raising was incredibly important because these are different dimensions of saying that approach or study or attempt is well better or in a way. So in cognitive science, I think in general it's a very non-trivial question. So because I think I have to think more about this, but I think in cognitive science, in cognitive psychology, it depends on how foundational our approach is. So if we are using, if we are generating very concrete applications of, let's say, diagnostic tool for neurodegenerative for diagnosis of neurodegenerative impairment, so that I think we might lack a nice kind of coherent grand theory, so the theoretical support might be lesser. Whereas if we think about, let's say,
Hey, can I interrupt you there just to so I understand well? Are you saying that for such a practical application, only performance counts? Is that your
no,
claim?
no, absolutely no. I just think that they vary. I just think that that the more applied approach we are examining, the let's say the more performance oriented it is, and I think it is. I mean, you just you well,
Or
it
are you
works, and it's sort of it's fine. I mean, more most extreme cases, of course, is a neural network approach where people are happy about the outcome, and they do not think about, let's say, cognitive um, uh, um, uh, let's say, correspondence of all that is simulated, for instance. But what is one of the another ideas that came to my mind is also that the more actually there are very few grand theories. So I mean, if you think about these large theoretical models, I mean, in the sense of theoretical models, so they are I mean, in cognitive psychology, there are very few grand theories. I mean, if you think
Do
about,
there have to be?
well, I think it'd be cool. I think it. Then we could think of those macro level theoretical frameworks. I think the difference between now and, let's say, 20 years ago is that in 20 years ago we had uh, quite a few nice grand theoretical models that could be used, as you mentioned, theoretical theory support. You can put those theories together in order to generate large kind of puzzle.
You can the way I intended theory support is you can also think of it in pretty humble ways, in pretty simple, small ways. So suppose you take these simple cases of you know these programs that try to separate wolves from dogs, right? So these people reach good performance. At some point, they had really good performance. They thought they could do it really well. Then people started probing. And what they found that if you inspect very closely how the model works, what the model does in closely manipulated situations, turns out that all they do is separate snow from no snow, right? If there was snow, then they said wolf, right?
Yeah.
And I'm simplifying slightly, but so there was so the factor snow had a very large weight, and of course it shouldn't have, because next year you might want to use the model in a country where it never snows, and then your model is completely worthless, right? So I would argue that even in the most practical of situations, you should care about much more than just performance, right?
Absolutely. So I think this is a very important point about thinking and comparing different approaches, especially in the time of large language models, so people are just using them without even thinking the background issue. So which is better? In which sense better? I mean, this is a kind of I mean, I think in cognitive psychology and cognitive science, the study is probably less kind of less weird than if you think about computing science. And there is, I think, Gontis is a computing science colleague in a hardcore sense of the word. Is raising hand. So Gunz, go ahead.
Thank you very much for I think it's a uh, very valuable perspective, and I'm trying to think about, well, does uh, how could we apply some of parsimony to neural networks? I mean, the trend now, of course, is that larger and larger is better and better, and actually training more data, it gets past this problem of the wolf and the dog. It learns to distinguish objects, and it learns to distinguish features of objects, and eventually it's I guess I want to try to defend the large neural networks a bit, because I do think that there's something going on that's valuable there. But the question is explanatory and theory based. We're not really at the point of having a good theory of how they're working internally, but that's true of the brain as well. So while I think the parsimony, the elegance criteria are very important for a theory. Um, um, I think there's something more about sort of the causal mechanisms, maybe that's what the theory needs to come down to. If it's a super elegant theory, but it doesn't fit, and I think this was in some of what you presented. If it doesn't fit sort of some intuitive ideas of how it could be happening, then maybe it's not a very good theory. So I'd like to hear, how can we bring the large neural networks into this vision?
Yeah, it's a good question, right? What I see in my own group, in lots of other places, is that there is quite a lot of thinking along that is consistent, let's say, with what I'm saying about parsimony. So some people who work with neural models, for example, are worried about energy consumption. And from that perspective, they want to reduce the data a little bit. I noticed that this recent Chinese model, I forget the name now, but the one that we learned about a few weeks ago, right?
Yes, DeepSeek, yes.
The DeepSeek. One of its striking features was that it was learned on far less data, and that received a lot of attention. People who were always a little bit more on the theoretical side of the neural thing um, uh, have always pointed out that neural models use so much more training data than humans in their lives that makes them a little bit, yeah, that's a little bit undesirable. What I see, for example, there's a new project here, a new starting grant, ERC starting grant, which is so it's called the Data Divers Grant. So the whole premise there, which I understand represents a growing set of people in deep learning, which focuses on the data. So which says, wait a minute, we'd like to learn from less data. We'd also like to learn less bias, right? All kinds of unpleasant biases or just incorrect biases are learned from data. And that's because we learn from the wrong data, right? Wouldn't it be nice if we could learn from data that was not prejudiced against women, not contain misinformation, etc., right? So the whole premise underlying that project is let's try to become much more precise about data. Also precise in the scientific sense that, right, if we want our data to learn certain things, let's make sure that certain situations, right, that all possible combinations of factors are there in the data, not just rely on, oh, it's big data, so it will all be there, because then certain things might still be much more frequent than others, right? So try to curate your data in the best possible way, right? There's more than that. So in one slide, I'm not sure whether it's useful to bring it back. I referred briefly to some older work in the neural domain on data pruning, for example, where people from a different perspective has said, yeah, these models that we make are so large, wouldn't it be nice to also be able to have always a much more simple version of each model, right? That we could then try to combine with explainability, right? I haven't said anything about explainability in my talk, but of course that's, yeah, an attempt to make these models more transparent and less opaque. Yeah, so sorry to ramble on, but I think, right, that in that space that you indicate, right, neural and smaller, there's a lot of work going on. It's all relatively early, but there's a lot.
Yes. Actually, I think there's another goal that some people have, at least, which is to get to the point where so maybe you need to, maybe the way you start is by training a large model on a tremendous amount of data, as they are doing now. But a vision would be that it becomes able to learn after this initial pre-training, that it could start to learn the way that humans learn, so that then it could
Right.
learn from a small number of examples, and then you're
Yes.
getting to the point where you can start to apply some of these criteria to this stage of
Right.
learning.
Yes, yes. That's a good point. You could point your lens at several stages. Yes, the fine tuning.
One remark about DeepSeek you mentioned. I heard there are strong indications that the Chinese used open AI data illegally, so they are investigating it now. So if that's the case, then it would be a very unfair competition.
True, but the response was telling, right? Because this was something that people really liked. Even the people who use deep learning, on a daily basis, they were excited by the prospect of needing less data.
Yeah, I think.
Or wrongly.
And then there's the question of unfair versus in violation of the terms of service or something like that.
Right.
You know, is everything that OpenAI trains on fair? You know, it's like
Yeah, exactly.
Okay, so I think we are over time, but it was very, very interesting, and I have lots of afterthoughts, and I think it's probably a good time to say thanks to our speaker again. Thank you, Kees. It was very, very, very nice, and
Thank you all for
we
some
do,
really thought-provoking questions and comments.
and we do hope to seeing you someday in Riga. I mean,
Indeed. As right, we've done before. Yeah, I hope.
exactly, in a co-presence again.
Yes,
So.
exactly.
Thank you so much. It was very good, and thanks also to the audience. It was wonderful questions, and yeah, well, we had a long and a very multifaceted day, and yeah, well, thank you so much, and looking forward to seeing you all in physical co-presence. And thanks, Keith. You were the peak of today's conference.
I doubt it. Enjoy your
Ja.
evening.
Thank
Thank you very
Nochmals
much.
bedankt. Tot ziens.
Thank you.
Thank you. Bye bye.
All right.